welcome to Quantum Photonics. Haptic devices have revolutionized the way we interact with technology by providing tactile feedback. Traditionally, these devices rely on mechanical actuators to stimulate the skin, but their range and effectiveness are often limited. On the other hand, electrical stimulation of mechanosensory neurons can mimic mechanical force, but usually requires high currents, leading to unwanted side effects like pain. In a groundbreaking study, Blau et al. Introduced a novel electrotactile device made from a conductive black copolymer arranged in a serpentine shape. This design allows for microscopic conformability with the skin, enabling the device to deliver stimulation at very low currents. Impressively, the device can switch between pressure and vibration sensations simply by altering the signal frequency. When tested on human participants, it is demonstrated safe and reliable electrotactile stimulation, making it a promising development for various applications, including human-machine interfaces and prosthetics. So, I have a lot to say about this work because this is very interesting. We try to invite our guest speakers to talk about this because, their work is indeed very promising. I will introduce first Ab- Abdulhameed Abdal, who is the main author of this work. He is a PhD candidate at the laboratory of Professor Darren Lipomi in the Department of Chemical and Nanoengineering at the University of California, San Diego. His research focuses on the design of bioelectronic devices that can be used for skin-based haptics, wearable electronics, and implantable medical devices. Abdul earned his BSSC and MS in Mechanical Engineering from Drexel and the Loyola Marymount University, respectively. And prior to joining UCSD for his PhD degree, Abdul was a research associate at the Florida International University in the Biochemical Engineering Department, where he was advised by Professor P.M. Raj. There he worked on electronic packaging for wearable electronics and power data telemetry for neural implants. He contributed to several conferences and wrote a chapter in the book Wearable Antennas and Electronics, edited by Professor John Volakis. Abdul is the recipient of the prestigious Bridging Grant from Kuwait Foundation for the Advancement of Science, or KFAS, and he had won the first place in the National Nanotechnology Entrepreneurship Challenge. Dr. Rachel Blau is a postdoc fellow at the laboratory of Professor Darren Lipomi in the Department of Chemical and Nanoengineering at the University of California, San Diego. Her research focuses on the design and synthesis of state-of-the-art conductive and stretchable polymers that can transmit tactile feedback, for example, haptics for human-machine interfaces. These materials are studied as tools for wearable and implantable sensors to understand neural activity in high resolution, and these materials have exceptionally broad areas of application in the biomedical field and could potentially be used for medical training, remote patient visits, physical therapy, robot assisted surgery, and prosthesis design. Rachel earned her Bachelor of Science in Chemistry from the Bar Ilan University, her pharmacy uh, from the Hebrew University of Jerusalem, and her Master of Science and PhD in the Medical Sciences at Professor Ronit Satchi Fainaro Lab at the Department of Physiology and Pharmacology at the Sacher Faculty of Medicine, Tel Aviv in Israel. There, her research focused on smart polymeric probes for companion diagnostics and more accurate excision of tumors during image-guided surgery. Rachel received several prestigious awards and fellowship, among them the Marie Sklodowska-Curie Actions postdoctoral fellowship, and before that, she received the Zuckerman CHE Israeli Women Postdoctoral Scholarship. She was also elected as a Future Faculty Scholar Class 2021 by the American Chemical Society, Division of Polymeric Materials Science and Engineering. So, yeah, we are even more interested to hear about the presentation, knowing the backgrounds of the speaker that we have here. So, without further ado, I am very glad to present to you Rachel and Abdul here in Quantum Photonics. So, welcome, Rachel and Abdul.
Hi, Cecile, and everybody in the room. First of all, do you hear me well?
Yes, we can hear you very well.
Oh, okay. So thank you, Cecile, for the kind introduction. I would like to also thank you for inviting me and Abdulhameed here, and for your great hospitality. And we are so grateful for the opportunity to highlight our research and scientific journey, and this work that we did together with Abdulhameed, which is also a first co-author on this work, that focuses on the biocompatible polymer conductors for communication with neurons. So, Abdulhameed, so please feel free to hop in during the presentation or during the question session later on. And I will
Yeah, hi.
start. Yeah,
Thank you, Cecile, for the invitation. And yeah, Rachel, the floor is yours.
thank you. So I will go for the next slide, slide number 2. I will talk today about biointerfaces for communication with neurons. So our body is constantly connected to the outside world by seeing, hearing, and touching. And the technology has evolved greatly by replicating what we can see and hear with audio and video settings, and even way beyond the frequencies we can detect with our human senses. And I will start with introducing a very well-known human machine interface that we all use daily. So just as an interface, what it is in its simplest, it's a method to interact between two entities. So when we think about human machine interfaces, we think about smartphones, laptops, tablets, um, and we constantly communicate with electronics during our daily life tasks and work, or for fun with games. But it's also very essential for professionals in the medical field that use biomedical technologies. So, for example, as you see in the slide, the medical team can use a variety of electronics during minimally invasive surgery, during medical training, as you see here, uh, for medical training during combat, um, or for rehabilitation patients that need prosthetics. And in the lab of Professor Dan Lipomi, we believe that the current missing uh, ingredient for next generation technologies for diagnostics and treatment is the implementation of tactile or touch feedback that can deliver information through the experience of touch, meaning haptics. So, for example, in minimally invasive robotic assisted surgery, it may enable the surgeon to feel the tissue without actually touching it, since he operates it remotely with the laparoscopic arms, as you can see here in the gray rectangle. It also may improve medical training. It may enable remote medicine. It can restore the sense of touch for amputees. It can create medical records of touch and palpation. And ultimately, it can lead to superior patient outcomes. And I will go to the next slide, to slide number 3, that shows that the technology for replicating audio and visual cues have evolved tremendously. We can replicate the visual and audio signals very well. So if we look at the evolution of screen development, the conversion of engineering and chemistry tools have advanced the field tremendously, from big and bulky screens to thin, efficient, and even flexible smartphones that we can hold in the palm of our hand, and can transmit the information from the outside world very accurately and realistically. But in terms of haptic technologies, which are technology that involve with a sense of touch, we are lagging much behind. And the most common technologies for application of the sense of touch I will call from now on haptic technologies. are produced by mechanical actuators, as you see here as at the lower panel. Um, so the primary function of such devices is to deform the skin to produce various tactile cues such as buzz or rumble or click. However, these motors are, as you can see, bulky and sometimes complex and costly, and the variety of sensation is limited. So another area of intense research is using electrical cues to stimulate the sense of touch, using lighter materials without bulky motors. And here, for example, you can see on the right former work from our group that combined these two modalities, the electrotactile and motor actuator on haptic glove. And in order to have a wider gamut of sensation, the authors used two modalities of motors and electrotactile. And the next goal that Abdul and I pursued in this project was to create one material that can enable multiple sensations as a stepping stone for long-term vision to create a realistic haptic technology that can deliver this information um, that is recapitulating object from the real world with high accuracy. Um, and we call it realistic haptics with this vision of recapitulating the real world in the technologies. And I want to go to the next slide, slide number 4, to show you where I started the project. So the project had the goal to have organic actuators for biomedical haptics. And when I was visiting the group for the first time, former lab member of the group named Colin Keefe has just finished a project and published a paper that I was just introduced you in the former slide. And I have tried this haptic glove. Here am I standing with the glove, and you see the computer screen behind me with the AR VR system that I can see. And the unique thing about this work that I could also feel the object in the AR augmented reality room. So I tried this technology myself, and as you can see on the left, I could see this is an image from the paper of the panel of different sensation that I got. And another, the person that also photographs in the paper is a former postdoc in the group named Laura Kaiser. She developed the polymer, the conductive polymer that was used in this work, and today she is a professor in University of Delaware. Um, so when I tried this later on, I joined the Lipomi group in order to advance this technology further using one component of conductive material that conformed to the skin. And this is the project that I'm going to tell you about that we were working together with Abdulhameed Abdal. So to understand more about the sense of touch, I'm going to move to the next slide, slide number 5, and tell you what happens when we touch an object. So I will start with a simplified overview of the tactile perception. So our skin has multiple mechanoreceptors that are activated by a deformation stimulus. When our skin is displaced by an object, different force intensities or tensile movements will create different frequencies that will stimulate the mechanoreceptor. So different pressure or skin stretch or vibration or light touch, as you can see here on the slide, will activate the mechanoreceptors in a different manner. And this will produce an electrical signal that is transmitted by the nerves to the cerebral cortex, and there it perceived as a sensation such as pressure or vibration or other perception as a warm, cold, or itch, as you can see. And I'm going to do the next slide, slide number 6, that shows us that we can evoke that sensation artificially by external mechanical or electrical stimulation on the skin by wearable haptics that are placed on the skin. So for controlled optic feedback, there is a need to deliver the appropriate stimulus using different amplitude or frequency of the electrical signal. And the electrical current passes through the skin and evokes sensation by activating the cutaneous fibers or receptors. And I'm going to do the next slide, slide number 7. So as you can see here, there are several examples for motors that uses force that stimulates the mechanoreceptors in the skin. And as I mentioned before, and you can tell, they are quite bulky and complex, which might reduce the compliance of the wearer. And if we go to the next slide, slide number 8, the lower panel show that advances in material science has enabled the development of sophisticated electrodes that can deliver electrical currents to the skin, that can also open ion channels and propagate action potential, which results in a repolarization in the somatosensory nerves. And in a simple words, it results in touch sensation. And this technology is called electrotactile stimulation, as the stimulus delivered by electrical cues. So when you think about electrical cues delivered to the skin, what does it make you think? Do you think it's pleasant? You're not sure, right? It might be a bit of painful. So, well, this is indeed a problem for some systems that use this technology. And I'm going to move for the next slide. And introduce additional limitations for electrotactile stimulation for haptic effect. So it might produce a range of sensation which are inconsistent between users. This might be due to differences in skin morphology or unequal hydration, which affect the contact impedance. So when we think about electrode that is placed on the skin, it's very important to look at the contact between the electrode to the skin. Because between the electrode, there is an impedance that is the resistance of the interface between the skin and the electrode, and it might result in higher currents and voltages that are needed for the stimulation, and also lead to a painful sensation. So there is a need to create a material that is highly conformal to the skin and avoiding those air gaps that hamper the charge transfer from the electrode to the skin. And with this, I will go to the next slide, slide number 10, and I will introduce the goal of this project. So we wanted to tune the haptic sensations using conformal electrodes. And our approach was introducing a single component made of PDOT, which is a champion material in bioelectronics. It has a good electric conductivity, and it's a biocompatible. And the formulation can be using dry electrodes, and it's also commercially available. This is what makes it very, very widely usable. And another goal was to use to fabricate a soft and stretchable material with engineered design to enable current localization and variety of perception. And as you can see here in the example, we used the stretchable electrode with different shapes or form shapes and sizes. And I will explain how we did it together with Abdulhameed. So there are multiple, I'm going to introduce the next slide about the demands for the integration of haptic feedback systems in skin interface application. And there are multiple demands for the integration of haptic feedback systems in the skin interface application. The material has to be conformable to the skin, meaning no air gaps. It should be comfortable for the usability of the wearer. It should be stable for long term, and it should be deformable to the skin. And another very important characterization that is required is since we deliver electrical current, the material should have high capacitance too, in order to inject higher currents as well. So when we look at the conformability, I'm going to introduce the next slide, slide number 12. We we look at the mechanical properties of the material. Um, and the mechanical properties of the materials should be very similar between the skin and the electrode. So if you look at the scale with the Young modulus, which is the metric to measure this mechanical properties of different material, conductive common metals are usually rigid and made of metals such as gold or silicon, and they cannot totally conform to the skin surface, which will cause unstable electrode skin interface. So the compatibility with the human skin is highly important here. And we want to narrow the gap, right, between these conductive metals to the skin, which has a several order of magnitude difference in modulus. So the next slide introducing the organic materials. So what are organic electronics? These are materials that made of organic molecules, but they're also conductive. So slide number 13 shows the champion material called P.PSS, which is a conductive polymer. And it's not as conductive as those metals, such as gold or silicon, but the mechanical properties can be tuned. And we can narrow the gap between the elastic modulus of the commonly used conductors to the skin. However, I mentioned before that it's commercially available, but you can see in the next slide, slide number 14, that unmodified P.PSS commercially available is in reality brittle, and it's hard for this unmodified material to accumulate to the strain of the skin without any additives. So I'm going to move to the next slide and introduce you current approaches to enhance the stretchability of this commercially available P.PSS. So one of the strategies introduced in slide number 15 is blending this P.PSS that's showed here in blue rectangle with additives. So those additives are small molecules that act as a plasticizers, and they make the material more stretchable. A different approach is to deposit it on elastomers such as PDMS, or engineer a serpentine shape, a curved shape that accumulate the strain by the 4 factor, or to molecularly engineer the structure to make it intrinsically stretchable. So each method has its own limitation, as you can see in the next slide, slide number 16. So the blending approach, the first on the left, might end up with leaching of the additives, which results in sometimes toxic material leach out to the skin area, and sometimes also loss of function. And the deposition of on elastomer or in plane serpentine has also limited stretchability due to intrinsic brittleness. And the last approach, using intrinsically stretchable material, can accumulate strain nicely. So our approach was to combine the 3 approaches, as you can see in slide number 17. So we combine both engineering this material to make it intrinsically stretchable and deposit it on a elastomer, PDMS elastomer, in a serpentine shape to get the more stretchable and more conformal to the skin with using no additives. So it can have a long-term stability. And the next slide, I will introduce our hypothesis. So the skin color slide introduced that we hypothesize that tissue-like material with the intimate contact with the skin will result in a tunable sensation while applying very low current amplitude. So as you can see here, the material should have a really good contact with the porcine skin. And I'm going to introduce the next slide of our methods of how we did it. So we first synthetically tuned the mechanical properties of the conductive polymers. This is the synthesis scheme of libraries of polymers that we took the backbone and we modified it with a soft segment to add stretchability. And the soft segment that we chose is called pipegmima polymer. It's soft and it has a bottle brush structure that is inspired by nature, by the proteoglycan aggrecan that is located in cartilage, human cartilage, which bear a lot of pressure. And we looked at different ratios between the soft to the conductive part. And I'm going to go next to the next slide to show you the differences between the ratios with more appealing look of the different solids that we got. So for different ratios between the ionic conductive part to the soft part, we got different solids. You can look at on the left at the powder, or as we go to the right with increasing ratio to up to 1 to 6, we have a more gooey solid that is more adhesive and more softer. And this can be the base of the synthesis of the conductive polymer. So the next slide will show you, slide number 21, how this material looks when it's conductive. So when it's conductive, it gets a very dark color, dark blue, shown almost black. And our best ratio, our best material or block of polymer that we got was ratio 1 to 6, and we called it block 6, as you see. And this material had the lowest elastic modulus, as you see on the left in slide 21, but it also had the highest toughness, meaning that it can bear much higher stress. And you can tell it by also the curve that shows stress strain curve on the right. And another important consideration for conductive materials is to have a stable resistance under strain. And you can see here the stable reading of the resistance versus the strain. And another important consideration was that we could enable a large batch synthesis and a very facile fabrication of flexible films, as you can see here, by drop casting and curing a film and a very flexible material. And with that, I will go to the next slide to show you the molecular structure that we simulated by molecular dynamics, that shows that this like light pink soft edges are made of the pipegmima, and the conductive part in red and blue are in the core. This is, you can see in slide 22. So we also confirmed this molecular dynamic simulation with chemical characterization called XPS, where you can see that the conductive part is at the core by the fact that the intensity of the detection is very low, and the fingerprint of the pipegmima is very high intensity, meaning that it's more closer to the surface, meaning it's on the shell. So this was a nice correlation between molecular dynamics to our chemical characterization. And on the next slide, I will show you some results that show another important characterization that I mentioned in the beginning from the properties that are needed, for example, high capacitance. So in order to measure the capacitance, we used electrochemical characterization techniques. And because the soft part of the pipegmima here in purple has some oxygen groups, it can enable also interaction with ion and ionic conductivity in addition to electrical conductivity. And this might enable higher capacitance that can be shown in slide number 23 in the larger area under the cyclic photometry curve, or on the right in higher slope for different current density versus scan rates. So with this characterization of conformable material with higher capacitance, we moved further to the synthesis and from the synthesis to scalable fabrication of this conformal P.PSS derivative. So the process was dispersing the block 6 on a mold, curing it, and then use laser ablation to choose the shape that we want, the shape that we need for different location on the skin. And here on the left, you can see two of our talented undergrads. On the left is EQ, that is drop casting the block 6. And on the right, there is Jason Chen that holds the electrode that he fabricated. He stretches it a bit and show you how it accumulates the strain. And in the middle, there is like the actual process of peeling off the sheet after laser ablation, and you can see how facile it is, and allowed us a high production rate of those electrodes. And with this, I will move to the next slide of showing the intrinsically conductive and stretchable material enables the conformal contact with the skin. So the low elastic modulus of our material allowed us for significantly greater conformal contact on the surface of the skin, as you can see here in the lower panel of slide 25. And you can see the difference between the film of the commercially available and the upper panel on slide 25 that is placed on the skin without actually making contact or deformation, as opposed to our intrinsically conductive and stretchable film that is deforming to the curvature of the skin and make much better contact with the porcine skin. And this is probably due to the similar elastic modulus that you can see on the right. So the elastic modulus of our material is much closer to the skin. And another important consideration is the impedance, as you can see in the upper graph, was stable up to 30% strain, which is the strain that is desired for application on the skin. And the next slide, slide number 26, show the difference of zoom out of this material on skin. So it's a bit hard to see here, but you can tell that some part of the electrode in the upper panel is not really placed on the skin, and there is a big air gap as the optical microscopy shows, as opposed to the lower panel that has a very good contact with the skin. And when we peeled it off or applied force for the upper direction, it was harder to peel off our material, which makes it work on formal and even a little bit adhesive to the skin. So in order to relate the parameters of electrical stimulation to the sensation perceived, we performed psychophysical experiments on a group of participants. So psychophysics is a study that of relationship between physical stimuli and the sensation and perception that they produce. And we designed a set of psychophysical tests that will characterize key elements in electrotactile stimulation, including pain and detection threshold, the perception quality, the spatial equity, and the contrast discrimination, as you can see here in slide 27. And slide 28 shows the actual settings that we did with human subjects. So you can see Abdulhameed here helping with instruments. I'm sitting here with the computer, with the scripts, with the scrambled trials. And in the middle, there is Anthony Navarro, which is another talented undergrad that helped a lot with the electrode fabrication. And you can also see the electrode on his forearm, the electrode that was used during those experiments. And the next slide, slide number 29, we started the psychophysical evaluation with the pain threshold that measured by applying biphasic current stimulation from 10 microamperes to 250. And this analysis of the results and the psychophysical part was done with collaboration with Professor Ronkeru from the University of Amsterdam. And measuring the pain threshold enabled us to know if participant might feel nauseous or subsequent on subsequent tasks. So it was either go or no go, because if they would feel pain, we would not continue this the psychophysicals experiments. So it was a very important first step. So and luckily for our we were very happy to see that, as predicted by the pain threshold, all sensations were reported to be very comfortable or neutral. And fortunately, the highest intended stimulation current for the detection threshold experiment was four times lower than the lowest pain threshold of any participant. So as you can see in slide 29, the like the pain threshold was much higher than the current that we continue to do the experiment. And I'm going to move to slide number 30 to show you the quantification of the detection threshold. So in order to detect the threshold of sensation, we used a two alternative force choice design to measure the accuracy with which the participants could identify which of two electrotactile devices had been stimulated. And we got a very high accuracy of the lowest threshold detected of 6 microampere. And to our knowledge, 6 microampere is among the lowest sensory detection threshold reported for an epidermal electrotactile device. And this was really good news for us in this project, since if you can see here the bar on the left in slide 30, our threshold is much lower than other reported electrode in the literature that goes from 0.5 to 3 milliampere, which is like 3 order of magnitude higher. So with that, we were very happy to have a very low threshold and to suit the threshold of current for each participant to have a more accurate measurement of sensation. So I'm going to move forward to slide number 31. And in following experiments, we were looking for the quality of perception, meaning what sensation are perceived by participants for different stimulation parameters. And we accounted for individual differences such as skin morphology or hydration by applying current amplitude equal to 1 time of the threshold, 2 times of the threshold, or 3 times of the detection threshold for each participant, rather than applying a fixed current across participant, as I mentioned earlier, to have a higher accuracy. And across all the combinations of frequency and currents of electrical stimulation, the participants predominantly experience the sensation of either pressure, as you can see here in slide 31, colored in red, or vibration, that is colored here in dark gray. So in less than 5% of the trial, a different sensation was reported, as you can see here, as warm or itch. And overall, the participants were significantly more likely to experience the vibration at higher frequencies, as you can see here, towards the 50 and 100 hertz, and pressure at lower frequencies of stimulation, as you can see here, towards the 1 hertz. And I'm going to move forward to slide number 32. And our model predicted that the crossover point at which the participant first began to report vibration more often than pressure is 6 hertz. And this was very interesting because the frequency of the crossover point happens to correspond with the frequency at which other rapid adaptive mechanoreceptor fibers that are sensitive to low frequency vibration become more sensitive to vibration than other cells called Merkel cells, which typically respond to sustained pressure. Um, and so it might show us that there is kind of equivalence between our electrical stimulation to the mechanical stimulation at a given frequency. And I will go to the next slide, the slide number 33 of the conclusion and outlook. So just to sum up the research that I introduced you today, um, I introduced you an integrated strategy that include polymer engineering by synthetical chemical synthesis and device layout engineering and psychophysical thresholding based on signal detection theory that can be used to overcome the occurrence of pain, desensitization, and lack of realism, and participant to participant variation in haptic technology. And with that, I'm going to go to slide 34 to basically thank all our collaborators, to thank our supervisor, Professor Darren Lipomi from the Department of Nano and Chemical Engineering in UCC, our wonderful group members, um, our collaborators, Professor Shadidaya from the Department of Electrical and Computer Engineering in UC San Diego, Professor Ram Karu from the University of Amsterdam, and her talented postdoc, Nicholas Root, that had done a tremendous work with statistical analysis and a lot of the psychophysical um, advices for the experiments, and our magnificent crew of undergrads that did so much work to make this happen. EQ and Anthony Navarro and Jason Chin and Jennifer Lee. And of course, thank you to Abdulhameed Abdal, that is also the first co-author and was leading with me the project. And I would like to finish with the vision. This is slide number 35. This is the vision for the implementing the haptic technology, the technology of the sense of touch, with a lot of technology that is a part of a lot of aspects of our life. So I took the two photos from HoloLens. This is a real lens that it's a real product that makes augmented reality for education or construction. And imagine that this technology will be implemented with realistic optics, and we can we can feel the object that we can see in the future. Another aspect that is very important that can be benefiting from haptic technologies is prosthetics. Um, Imagine prosthetics that can feel and restore the sense of touch for people that lost it. And a very long-term vision for prosthetics with the advancement of bioconvergence and 3D printing is maybe one day we can complete a full organ that doesn't have only the anatomical structure, but has also the ability to feel. So with this, I would like to conclude, and I'm happy to to take any questions together with Abdulhameed Abdal. And Abdul, please feel free to add more comments.
Yeah, thank you so much, Rachel. And Abdul, before we open the floor to the audience, would you like to speak or add some more comments?
I think Rachel did a wonderful job of covering all the elements of our paper and the research that we did. But we're more interested in hearing from the audience if they have any questions regarding the paper or even generally about haptics.
Yeah, thank you so much, Abdul.
Thank you.
And yeah, I'd like to thank Rachel again for such a succinct presentation, and ending the presentation with a vision, as well as trying to address again, uh, bring to us the questions that they were trying to address when they made this research. So I am also very excited about the use cases and probably even use cases that we haven't even thought of as of now. It has so many applications and it will affect the way we play, we work, the way we eat, because it can be integrated to multidisciplinary fields that we have. So yeah, I would just like to also welcome Frank, our co-moderator here, and then there is Isabella who came on stage, and then there was Nas who might be coming back later on. So um, I'm curious on what was the amount of time that you had, considering that you already have this background in your previous studies, in your lower studies, and in your other labs. How long did this work paper? How long did it take to write this paper and have it published?
I think Rachel and I started this project about 2 years ago. Um, the works because we wanted to check the aspects of the material. Rachel already had synthesized a nice library of the material before, so we wanted to take advantage of the mechanical properties of what she synthesized before. Rachel, please feel free to add to this. And then we came up of an idea to use this material for electrotactile stimulation. But I would say it took about 2 years for us to actually come up with a nice utility of the block 6, which is the polymer that Rachel synthesized for this specific application.
Thank you. So, is this material available? For example, if I have an installation and I would like to use this material, and yeah, for an art installation, would this be available?
Uh, in terms of commercial availability, no. Maybe Rachel one day would consider that, but I think Rachel dedicated a lot of time. Like it's mostly synthesized in the lab through her experience, but it's not commercial available. But maybe something Rachel should consider one day. That's for sure.
Yeah, thank
But
yes, so here in Quantum Photonics, maybe one of the first rooms that we had here in Clubhouse was about the work of Miguel Nicolelis, who is a pioneer in brain-computer interface and whose students formed a company which Neuralink bought later. So
Mhm.
during his first experiments were in uh, actual execution of his experiments, actually, which was widely demonstrated. He made a paraplegic who hasn't walked or touched anything with his hands and foot, I mean without sensation, for about maybe 12 years. He made him walk in the stadium in Brazil,
Yeah.
using only these exoskeletons, and also only using his brain to make him walk. So the training that Miguel Nicolelis did was that he put just like a swimming cup in the head and on the skull, and of course he used electrodes on it, and he trained the one who's going to use brain computer interface to walk for about 8 months using virtual reality with the electrodes on his skull. So, as I could see in the presentations that you have, you considered a lot of things. Like, for example, the kind of material that you will be using, will be it be effective, sensitive, or yeah, will be it be the better choice to use for these haptics, and also so many things being considered, including the psychosocial uh, yeah aspect. So can you comment about this? And I just want to say that the training for that took about 8 months with such still very crude technology when people were not talking about virtual reality then. So I think your research will try to fast forward, experiments or work like that in neuroscience as well. So any comment about this?
Yeah. I'm not familiar with the paper, but I'm pretty sure this is very interesting. The thing is that when you have electrodes that is in vivo inside the skin, probably the properties required are different than what we did on a skin surface. The issue that we found, Rachel and I, when we looked at the literature, a lot of the electrotactile that are on, let's say, electrodes that are placed on the skin layers, either the forearm or the hand, we saw that these electrodes are usually made from conventional materials. What I mean by conventional, they're metallic. Now, the issue with metallic materials is that they do not really conform to the skin given the elastic modulus. Now, if you have those materials for haptics, we're not saying that this material that we have actually induces the sensations. We're just saying that maybe a consideration to reduce pain sensations could take an approach with materials. And how we assume that is that a conformal material that is placed on the skin could reduce those air gaps. Now, air gaps could be an issue because during stimulation, you could have some discharges on the surface of the skin. And the better reduction of those air gaps that is usually very common with conventional materials such as metallics, we found that the pain thresholds are even magnitudes or at least one magnitude lower than the detection threshold. And this is when we decided, let's do some modulation studies. Let's try to ramp up the current. Let's try to ramp up the frequency and see how our participants feel. And this is when we saw there's some sort of normalization in frequency and some normalization on their subjective perception, which is basically between pressure and vibration. But when you consider this material in an in vivo more into like an implantable device, I'm pretty sure the consideration would be way different because you want to maintain properties such as impedances. Impedances vary a lot, even on the surface of the skin. And when an impedances vary a lot, you could the electrical waveform could vary. And if it varies, the change of perception could also vary. So maybe a feedback that controls the waveform as a function of the impedance is necessary. And I think a prior work has also showed that you can always alter the intensity of the stimulation as a function of the impedance.
Yeah, thank you, Abdul. Yeah, very great conversation with both of you, Rachel and Abdul. But I'd like to give the floor also to those who are on stage now, Frank and then Kevin and Nas.
Yeah.
Yeah. Uh, Frank, would you like to speak now? Then thereafter, I would give the mic to Nas and Kevin because that's the order when you came up the stage. If you want to speak now, Frank, just open your mic.
Yeah, thanks, Cecile. Yeah, yeah. Congratulations for the great work that
Thank
your
you.
team. Yeah, the very interesting research. I have a few questions. For Risha and Abdul. What I understand from the very beautiful slides you were able to share with the public, with the club. From what I understand by reading the slides is that you were able to add a long copolymer to the existing PDOT PSS, so that the conformality, I mean, with much better, I guess, toughness or softness, so that the assumption is that this will improve the sensor performance, right? So apparently you have shown with it improves also the bonding. I mean, probably more what do you call hydrophilic type of, which is good for skin, I assume. I don't know if I forgot if PDOT is more of the other side, hydrophobic, but I don't know. So I do see a slide with a block 6. So this is on the slides number 20. This seems to be the highest ratio added to the specimen that you tried. What if you go higher, even in weight percentage? Have you tried that, or is it already? You've shown that this is the optimal already? And also, for the so that apparently the with the matrix of this new added long polymer, the so the target of the, I guess, market or performance is for the crude touch, right? So uh, is it for the future that there will be fine touches, like even uh, 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 so if, right now I see it as the size of the it, it's it is a circuit in one per sensor, right? So possibly in the future, in order for fine touch, that will be array or finer matrix. I don't know if that's in the plan. And also, it's very interesting education on the number of different type of sensory cell cup, the Messenger, the Merkel, different sensation modality. Right now, I see on the slide 31 that right now it's good for pressure and vibration of certain frequency. And for this particular slides, I was wondering if, in theory-wise, we know that there's this Frankel-Weber psychophysical laws for there's a kind of exponential. So it's like we're waiting by hand, right? So the, we are very good at tuning into the finer scale, and it seems to be a logarithm. Is that built in this? I guess probably 3 or 4 questions in there. Sorry if
Yeah,
you want me to repeat. Yeah.
that's fine.
I think
Rachel,
I can take the first part of the question. Very good question. You started with why did we try the 1:1, 1:2, 1:6, and if we tried further, like higher ratio. So this is a great question. Um, so we it's this work is the follow-up work after a previous publication that we explored very thoroughly what will be the ideal ratio between two parts. So you said correctly that we use the derivative of p.pss, the commercially available, and the change was the covalently attachment of the soft part with which is the pipegmima. So we tried the different ratios and which are introduced in slide 20 and also in slide 21. And the ideal ratios of 1:6 was the ratio that we chose to continue, because when you make a very long soft part, you should also take under consideration that this is a non-conductive segment. So you add a lot of non-conductive, not electronically conductive. It is ionically conductive, but it's not electronically conductive. So if you add a very high amount, you will hamper a lot of the electrical conductivity of the material. So we stopped at the sweet spot, which was the ratio of 1:6, that enabled us the best fit to the skin, the closer elastic modulus that resembles to the skin, but also good conductivity to enable the performance for the later on haptics electrotactile stimulation. Regarding the next question, if Abdul remembers,
yeah,
feel free to hop in.
I think the next question was about the integration of a couple of electrodes. That's a really good question. So in our current research, we did not integrate multiple electrodes in a specific format. However, we did a couple analysis to show that this is actually possible, and we show that through two different results. One through the contrast discrimination is the just noticeable difference, which also answers the third question, which is the Weber-Fechner's just noticeable experiments. Basically, what we did, we fixed the positions of the electrodes, and we increased the currents, and we saw how participants could discriminate between two different electrodes stimulating at the same time. And we saw that, yes, this is actually possible. If we want to integrate more electrodes in a specific area, we can actually do that, and we can see that participants could respond at a specific current, and increasing the stimulus doubled the odds for participants to feel the difference between the two stimulation currents based on their personalized threshold. And the second experiment that we did the spatial discrimination. Basically, we fix the electrodes and we bring them very close to each other, so we would know if we want to lay them out in a wearable, we want to know based on the size that we had as the electrode, which fits the average forearm of a human participant, how close can we keep those electrodes together, and how if they're that close, could these electrodes be distinguished based on switching their on off or both on, and to see if they can distinguish between those two electrodes given a specific stimulation current. And we saw, yes, they can actually discriminate them at a very high accuracy. So the question of integrating those electrodes on a larger scale in a wearable is possible based on the results that we found out. Does this answer your question, Frank?
That's great. Yeah. Yeah. Just quick follow up. I have experiences with many years ago that with a system called Phantom. Probably you're aware as well. Could you commenting on the? I remember that the experience is very good. With different simulating different textile sensation by dynamically moving a probe over some graphics of different textiles surfaces and stuff. That's a dynamic kind of your sensor should be capable, to be integrated right in. But in terms of a wider, products and application market, and I assume Apple would be the sponsor and related research, and many. It's a huge impact research. So could you commenting on that?
Yeah, good question. Phantom is very interesting. I think the vast majority of interest after publishing the paper, we saw a lot of people from the medical sector are very interested, specifically with teleoperation. Some also were interested in AR, VR. So why do I say teleoperation? A lot of the surgeons that use teleoperation have a bracelet on vibrotactile devices that's actually used through their training. So they get their notification through a bracelet that they have on their forearm. Now, vibrotactiles are, indispensable. This is found in our everyday. Specifically, a common example would be our phone. However, vibrotactiles sometimes could be bulky on the forearm, and we want more thinner devices. So one interest actually came in was that how can we integrate those very thin wearable devices if they could stimulate and they could avoid pain, can we find a way to integrate them on the fingertips? We can find a way to stimulate the fingertips rather than having the vibrotactile on the forearm as a bracelet. And we've seen that a couple of researchers actually reached out on how can we integrate this to have like a feedback system where the machinery that they're operating, whether it's a teleoperation or an AR VR, senses a specific, I would say, external stimulus, and then like for example, they have a sensor, and the sensor is digitized, and through this digitization based on the magnitude of the sensation, could we stimulate the electrodes that we performed and we showed to actually induce a notification on what they sensed through the equipment they're using, I would say. So we've seen a couple interests recently regarding this, and the best selling factor to having this haptic is basically the thin form factor when compared to something that could be a bit bulky to wear on a bracelet.
Okay, that's great. Did you mention Mayo? Did I hear you say the word? There is a product that is a bracelet that are using the EEGs, I think. MEG.
To be Yeah, to be honest, I'm not sure. I didn't mention Mayor, but I'm not sure if it is something they're developing in a bespoke manner in a lab, or they're using something that are commercially available. They just brought up the idea that they actually use it as a sensory substitution form to notify the surgeons during a surgery or during training. But I'm not entirely sure if it's something that is commercially available or not.
I see. Yeah, thank you.
You're welcome.
Yeah, thank you, Frank. So I think Nas dropped off the stage. I hope he will come back. So we have here Kevin, who has been waiting patiently. So I'd like to give the mic to you now, Kevin.
Oh yeah, now this is awesome because I used to work at Atari in the 90s. You know, we did a game called Lawnmower Man. You know, the Stephen King, short story and the movie, and that's about VR. You know, so that's some of the first VR stuff. And so I still have ties with that, but that's interesting. And my dad worked at Clorox for packaging science lab and all kinds of stuff with that as well. So this is kind of near and dear, but the only some of the main things I thought of right now is just hopefully you didn't cover it all. Is accuracy and consistency. Technical drawbacks. That can include issues with like sensors and actuators as well as compatibility and connectivity issues. And also to communication between haptic devices as well. It can be problematic. I've heard and systems. And then the other question is how does this relate to drones? I heard specifically. I heard about drone stuff. Oh, thanks.
Great, Kevin. Thank you for introducing yourself. It's very awesome that you used to work with Atari. That's very cool. In terms of challenges, but I think Rachel and I that integrating those devices could be a hurdle if we did not consider waveforms that change over time based on the skin perspiration. So your skin, the human skin, is uh, dynamically changing per day based on sweat. Now we did not consider how can we alter the waveforms. So if we want to translate this on something on a day to day, so similar to the iPhone or a phone, where whatever notification you have, the intensity of the stimulation is constant. You always feel this buzz through the phone. Now, to have this with the haptic that we developed or the material that we developed, we should really consider what are the changes of the human skin to accommodate the intensity of the stimulation. That's the first challenge, I think. And I've seen papers that actually tackle this challenge, but further research is required to see how can we modify this to make sure that the electrical parameters of the stimulation does not vary the intensity that we feel as a function of impedance. And I've seen some works that actually focus on that. And actually, one of the companies I've recently visited, Psionics, and actually show a very nice, interesting demonstration of this. Uh, the second question about drones, that would be actually really cool. I've never seen any of the electrotactile research with drones, but my only assumption that, let's say if you fly a drone, probably a haptic feedback would be something like an alert. Let's say if you travel in a danger zone, you'd get a haptic feedback, or no fly zone, you get a haptic feedback as a notification. You should, steer away from this zone or this area, I would say.
Oh yeah, and then, yeah. Maybe that has to do with vibration. Yeah, and I know you guys got the vibration as well. I heard. Yeah.
Yeah, that's actually really cool. I've never thought about drones before, but yeah, you could, haptics could be used for anything to deliver, a notification to the human body, instead of having something that is handheld through your, like, back to the phone, something that is handheld. You can always interface it, whether it's micro actuators through mechanical stimulation or through electrotactile. You can always have it on your skin, and this notifies you whether it's a drone flying in a no-fly zone, or a biomedical device that tells you if your heart rate goes high, or your glucose levels are a bit higher than usual. So anything, you can adopt the haptics in any field you wanna, to notify the user of any metric of signal that you are wanting to study, I would say. So it's more open to what you want to implement with this haptic module.
Oh, thanks a lot. Maybe I'll research the drones. Maybe I'll have a follow-up question if I see more stuff about the drones. Thanks. I was kind of surprised when I heard that too. So.
Yeah, that's actually really interesting. I've never thought about it. It's really interesting. I think the vibrations through the drone, given that I've tried it once, could be through the console. So like an Atari, or I would say a PlayStation, you get a vibration sensation through the console that you're trying to, or a controller that you're trying to maneuver through the drone. And I see why would someone would use that.
So I would like to reset the room. Yeah, we are opening the floor for questions and answers. And if you want to ask a question or do some clarifications, please feel free to raise your hand. And our guest speakers here, Dr. Rachel Blau and Abdulhameed Abdal, are from the laboratory of Professor Darin Lipomi in the Department of Chemical and Nanoengineering at the University of California, San Diego. So they are researching. Rachel is researching, and also, her research is related to the research of Abdul on the design and synthesis of state-of-the-art conductive and stretchable polymers which can transmit tactile feedback haptics for human-machine interfaces. So if you want to hear a detailed introduction of both of our speakers, please check our earlier part of the room to be able to hear about their work. And we are now speaking for those who just came in. We are speaking about their research on this, and you can see the link at the room chat. So, yeah, I just want to ask. I had worked also using HoloLens for a UN presentation before. It was about CRISPR, and the other one was about climate change and trying to look at the forests and of Brazil, and what do people feel, when the climate change is affecting this area. And CRISPR, of course, it was used just like more in edutainment, but an information about education using VR and AR. And I could see that while you're speaking, the potential for your technology will not only be applicable maybe to higher education and also very serious research, but I think it can also be applicable in terms of pedagogy to really learn the basic concepts in terms of trying to teach children, even children who have this early education. For example, in a Montessori education, they try to integrate touch, the sense of touch. So that's why they try to make children experience how to pour water, how do you feel about that, and how to touch sand, so that these children will be able to understand tactile sensation. And one of our colleagues in Singularity University, well, he is now everywhere. He is Shafi Amid, who is a surgeon actually. He is doing this surgery, remote surgery, using AR and VR. I wish I could invite him to understand currently what kind of technology, or if there are other haptics that they are using. So anyway, I think, and it has a lot of use cases from early education up to higher studies. So may you comment on this? I know that Rachel has presented some of this in her slides, but anyway, please make a comment.
Rachel, do you want to answer the question?
It's, you can go ahead.
Yeah. So the idea of using this with like on kids is very interesting. Actually, that's a very good idea. We've never thought about this, but to have kids feel the different sensations of touch, whether or the texture, is something could be in an educational platform. We actually consider using this not precisely for kids. We actually consider using this as a braille reading on the fingertips. So if we can make letters or numbers through electrical stimulation, basically, if we have dots of electrodes on a fingertip, and we've seen that before too, and we stimulate a specific characteristic or a symbol for braille readers to have those devices on the fingertip rather than indenting, or I would say moving their fingertip on a fine texture. And this is something I think would be more interesting to see if could the accuracy of braille reading on a fingertip through electrical stimulation is as fine as something that is well established. I would say having a blind person move their fingertip across a fine texture of dots rather than having something on a fingertip. But on considering having this with kids and to develop their understanding of perception, that actually would be a nice uh, idea to implement to teach young kids on what is tactile sensations and how can we feel or perceive a specific tactile sensations through different modality of haptics, whether it's mechanical actuators or even electrotactile.
Thank you. I think it's gonna
I,
be disruptive because basically during the pandemic, kids, when a lot of people were on a lockdown and they could not go to a face-to-face
mm-hmm,
interaction with teachers, even on early education. So they don't have these tactile experiences, and I think it's very important because maybe these kids will also grow up to be like a scientist, just like you, and if you even if you try to integrate this in an early experience on how to do surgery, or just like what Rachel was saying earlier on what Microsoft I think did about trying to do some holographic presentations in VR to study
mm-hmm.
the heart, for instance. So the higher we advance in terms of technology, the earlier we can train children to really understand it in a fun way. And anyway, because when they grow up to be adults, they're going to use the technology. So I
Yeah,
have very high hopes of the many uses of your technology.
yeah, yeah.
I
Well, we
I,
appreciate. Yeah, sorry, Kevin.
I see a hap kit. Oh no, sorry. I'll just say this real quick. I guess I think I have a bad connection, normal lately. I see a hap kit. Stanford professor Allison, Okamura is using a build-it-yourself electronic kit called Hapkit to create physical sensations using a programmable device. This is being used to teach a class in haptics, the science of touch. Hopefully you
Yeah,
heard that. You
actually,
heard that.
one of her students is actually a professor in a university and also teaches HapKit for graduate students. We do have this class at the university. It's interesting that at nowadays, because this is something new, especially with like skin integrated or skin interface bioelectronics, haptics is a new I'll say technology that people are using. Hapkits, yes, I we've seen it before. We've seen students learning this at an older age. I would say more or less they're masters and graduate students. But back to Cecile, I would say teaching this in the near future, I think, because those technologies are an emerging trend, I think in the next, 10, I would say 20 years, younger generations could be more exposed to HapKit or even, tactile modalities because maybe, in the next, I would say 10 to 20 years, the haptic technology, especially with AR, VR, or even educational platforms, could be shifting to a different trend. Especially, we saw how notebooks have been changing to iPads, and maybe nowadays they're finding a different way to demonstrate or to teach. Especially with the pandemic, we have the Zoom. We never considered that before. Maybe the way of teaching could be more in a virtual environment, and something that we should consider teaching our kids haptic modalities. Maybe in the next few years, the transition to educational platform could slowly could slowly I would say change into platforms such as virtual environments to teach kids, specifically like younger kids, in which they are not required to be at a specific environment or a specific class structure. They can do it more in a remote sense, I would say. That would be really interesting, actually. Never thought this before.
Yeah, thank you, Abdul. And as I mentioned earlier, the Rachel, we had other rooms which also talk about a similar product, but with very detailed considerations that you had, Rachel and Abdul. Yeah, this is taking it to a higher level and addressing the questions, in advance that others have not addressed. So, congrats. And Nas is here, back on stage. I'd like to give the mic to him.
Yeah, thank you. Thank you, Rachel. Thank you, Abdulhameed. I have two quick questions. Number one, are there any clinical, diagnostic, or therapeutic usages for this? For example, if it's an iPhone, can I use this touch signals to diagnose certain disease or conditions? That would be a huge breakthrough if it can apply to clinical or therapeutic medical applications. Any thoughts on this too?
Good question, Bob. I think what is possible is that, uh, m- let's say, if there's a therapeutic intervention, you need a feedback that notifies you of a specific bioelectronic signal. You can use any haptic module depending on the application, whether electrotactile, which we demonstrate in this paper, or commercial available actuators. Yes, you can use that to notify you of a specific, let's say, signal. And what I mean by signal, let's say if you are having, let's say, high heart rate or a high glucose, you can use a different device to measure the outcomes of those signals, and then and combine those signals with a feedback that notifies you, when this feedback could be whether our device or a commercial available device, to notify you of those signals, as a benchmark to if this is a normal signal, or is there something abnormal that you need to, visit a medical clinic or a checkup, based on that, I would say. So, is it something that we could use to diagnose? I would say no, more to notify of your diagnostics.
Thanks. I'm trying to bring good friend on stage because he raised his hand, but I could not. So, yeah, if you are listening to me, good friend, you can go out of Quantum Photonics and come back again. Maybe it's just a glitch, but I would very much like to have you on stage. Bob, can you see him on stage or, yeah?
I invited him. Yes, he's on stage now. Welcome, good friend. Okay, Mike to you, good friend.
Maybe please come closer because we could not hear you well. Yes, so yeah, uh, try again, please. Uh,
Yeah, I can hardly hear you.
If you have any Mac issues, good friend, you can feel free to write your question in the text, and we can try to answer that too.
Yes, so while we are waiting for good friend, I would just like to mention this is something that came up while you were doing your presentation, and while we are having the discussion, I was thinking about another use case of your research in artificial intelligence, because I have friends who did this. They are in AI, and they capitalized on the works of Paul Baccarita, who has been working on sensory substitution and tried to do an experiment using the tongue to be able to see. So, as Rachel had mentioned earlier, of course, the perceptions that we have based on our sensations have been considered. And anyway, what they did in trying to apply this to AI was that the electrotactile simulation was looked at the lens of enhancing human machine interfaces and advancing technologies of AI to interact and understand sensory information. So since they don't, AI does not have a sense of touch, probably it can add in the future to artificial data, or it can evolve a certain kind of training in artificial intelligence. So I think this has many exciting fields to go into. So yeah, good. Just please open your mic and try to speak if you are ready. Otherwise, I'd like our speakers to comment on what I said a while ago.
Yeah, I can comment. Yeah, thank you, Cecile. It's a really nice observation that there are so many fields that can enjoy or make a lot of benefit from the addition of the sense of touch of the or producing the sense of touch, and this is a really big challenge for the community that works on haptics and work on sensory substitution to just solve a lot of challenges because this transmission of sense of touch is so complex, and as I mentioned in the presentation, among other technologies, haptic technologies are very lagging behind with realistic sensation. So when you mentioned your the AI driven with the sense of touch, I guess that those technologies would like to combine it with as much as possible realistic sensation. And this is a big challenge that makes a lot of scientists a lot of work and career pursuing in this direction. So this can be really exciting advancement.
Yeah, I
Yeah.
think if you bring it further and be creative, you can make a startup and you will become really big. Because this reminded me of the work of Fei Fei Li, who brought us computer vision. So she was speaking about computer vision in terms of evolution before how it rose to a Cambrian explosion. And so
Yeah.
that's why we have our self-driving cars now and so many other things, because AI was able to see. But when she first discussed it, everybody, and including Andre Karpathy, was saying it's impossible, but they were able to bring that. And so I would like to look at evolutionary computing and also evolution, natural evolution in itself, on how we were able to evolve, senses in order to survive. And touch is a very important sense, even if we are babies, because basically, if you experience pain or heat, that tries to prevent you also from going into dangerous places or trying to injure yourself. And yeah, I would like to look at that level, because it has so many things that it can bring about. So I think it's very exciting, and I think that this is one of the most advanced research that I've seen in haptic technology. So I hope that you and Ahmed will try to lead this in the near future.
Thank you. Yeah, thank you so much. I totally agree, and it's a very exciting field, and I'm sure that Abdulhameed is agree with me, right? Um, please add your comments, Abdulhameed.
Yeah, actually, I do agree with Rachel. I mean, if we consider uh, using electrotactile in a wearable format to accommodate all the needs of, I would say, especially like in my field in the medical devices, where we are very reliant, for example, to devices such as the Apple Watch, in which it measures your heart rate and your steps. And nowadays, Apple is more interested in more in-depth analysis of the human body, and we could assume that one day they want to use the Apple Watch maybe to find a way to measure different diagnostic tools to extract the as much as they can from the human physiology. Now, the way they notify you is through their common vibrotactile system through the Apple Watch. Now, if Rachel and I find a way to implement this more in a thinner format using our technology, I mean, using this translationally would be really interesting. I would definitely agree with Cecile and Rachel. Maybe in the long term, using this, that would be probably beneficial to especially people who want something that is imperceptible on the skin, uh, uh, and they don't want using a watch or Apple Watch to communicate with the machine in terms of their own diagnostics or personalized medicine.
Yeah, thank you, Abdul. I hope that Good would be able to speak now. And I just want to say that, I think a lot of people are very interested to hear more about your work here. But we had been here for about 1 hour and 45 minutes. And as I said in our briefing, I would like to politely also ask you how much more time do you have for us, because we respect your time. And of course, we want you to continue the discussion if possible. But yeah, we'd like to ask you that.
Um,
Thank you. Yeah, sorry, Rachel, you can go
yes,
ahead.
thank you. We can do one or two more questions. Also, like, please, Abdulhameed, tell what you think.
Yeah, we can do one or more two questions, and also if any audience, if we didn't have the chance to answer their question or they have further questions, please feel free to email us whenever. Rachel and I are pretty responsive, and hopefully we can accommodate any questions or answer any specific questions anyone could have. We're more interested from hearing from your perspectives, so we can actually advance our research into different areas, I would say.
Yeah, thank you, Abdul, and thank you, Rachel. So, to everyone who just came in, and yeah, of course, you can listen to this talk. It will be at the bottom of the Clubhouse profiles of our speakers and also my Clubhouse profile. And yeah, it will be in the Quantum Photonics replay. But Bob is introducing our new YouTube channel in Quantum Photonics. He is editing this channel and he tries to sync the slides that we have into what our speakers are trying to explain. So you can just search for Quantum Photonics in YouTube. It's not that sophisticated yet, but we had started to collate maybe about more than 30 replays in YouTube so that it can be immortalized there and it can be more accessible to anyone. So, yeah, with that, I'd like to welcome again Good. I hope you have a better sound now, and Kyle, who had come on stage. And I think they will be asking the last two sets of questions. So, Good first. Good, are you able to speak? If Good can't speak now, probably he can write on the room chat, maybe. Uh, and there's Kyle, and finally there's.
Yeah,
Oh,
am I audible now?
yes, yes, we can hear you. Go ahead, Good.
Yeah, so I will just ask in short. So I was just reading the conclusion on the slide. So I'm interested when what do they mean by overcoming lack of realism?
Uh, can you repeat your question, Good?
Yeah, in
It's
that
not
slide,
clear.
that conclusion slide, they have mentioned this, overcoming lack of realism. So can they give some examples to that?
Yes, I think what Rachel meant by overlacking lack of realism is that we've seen from previous research that uh, electrotactile has not been, I would say, as dominant as other haptic modalities. The reason why is that people usually associate electrical signals, especially on the skin or the human body, as a shock, and there's this lack of realism also because there are other attributes to this, and this could be given that electrical stimulation could cause pain. Now, this is true. If you stimulate at a very high current, this could also be painful, even or fatal. Now, the thing is that if we find a nice, I would say, range in which we can use the stimulation very safely, and at a range that people could sense uh, natural sensations, and this is what I mean by natural. Could be a gamut of percepts. Could be pressure, vibration. Could be heat. Could be itch, rather than just pain. Then we could see some advances of using this technology. But prior to the previous years, I would say the past 5 to 6 years, a lot of those electrotactile devices shown in the literature show that there's a high dominance of pain, or there's a very short bandwidth between what you perceive as natural, and then you would quickly switch to pain. And we show that in our case, when we really consider the psychophysical analysis at a very low minimal detection, and minimal detection meaning you minimally sense the electrical signals, and we play with that range, you can feel the natural sensations. And this is what we mean by lack of realism. Up till today, there's still lack of realism of using those devices, given the probability of feeling pain using electrical tactile or electrotactile devices, I would say.
Yes, yes. Thank you so much for
You're welcome.
explanation and this wonderful presentation, wonderful work
Thank you.
also.
Thank you. Appreciate it. Thank you. Good.
Yeah,
Thank
thank you,
you.
good. Yes, so we'd like to give the mic to Kyle. Kyle, are you able to speak?
I will.
Go ahead, please.
Sorry, I hope I have a good connection here. I just want to say thank you. It was an amazing presentation. I may have missed this, but I your work for meditation. Just curious if you've looked into that.
Kyle, you were in the matrix for a little bit, so if you could try to repeat your question, that would be good.
Yes, so maybe Kyle could not connect very well. And I think there is a comment here on the room chat, which yeah, before Kyle comes back, and if Kyle cannot come back here, this will be the last question. This is from Mary on the room chat. Her question
Is
is,
this
any hope
better?
you can, Kyle, go ahead.
He's gone.
Yes, so Mary here at the room chat is asking, any hope you can offer people with centralized nerve pain or centralized in the brain? So, yeah, I'm not sure what she means, but maybe our speaker can get what she wants to ask. Any hope that you can offer people with centralized nerve pain?
Um, I'm not sure I understand the question, but I think I got a sense of what Mary meant. There's a people usually so electrical stimulation has been used for transcutaneous electrical nerve stimulation. So basically, if you go to a pharmacy, we can buy an electrode that stimulates either the neuromuscular junction for or even for pain reduction. Uh, I think the field of pain reduction or anesthesia or TENS, I would say, transcutaneous electrical nerve stimulation, is a bit different in terms of what we're trying to do in haptics. However, their stimulation amplitudes, from my understanding and through my experience of using it, they're typically higher because you need to uh, I don't understand the mechanism exactly how it works, but you need to stimulate at a higher current because you're trying to stimulate the neuromuscular junction to actuate, let's say, a movement. Or for pain in that case, is to reduce pain. I'm not sure how this actually works, but it could reduce pain through activating a certain type of receptors or not, or does it fog the brain? The exact mechanism is unclear to me, but I've seen people use TENS for pain reduction. Yes, that is true. However, it's kind of different from the field of haptics, I would say.
Yeah, thank you, Abdul. So, Bob, would you like to, Kyle, are you able to speak now? You will have the last question because it's getting late. But if you cannot speak now, Bob, would you like to read the comment of Kyle on the room chat?
Sure thing. Kyle mentions that meditation aids and devices also use haptics to guide users through meditation routines and enhance the user's mindfulness experience. So that's his comment.
Yeah, so, all right. So we're going to wrap up because, yeah, we've been here for almost 2 hours in such a very interesting room with great and, very well-rounded speakers aside from their specializations that, they talk to us about now. And, yeah, Bob, if you have if you want to speak or you have any message before we close the event, please speak. And Darcel, after you will close the room. In the meantime, I'd like to first give back the mic to our two speakers if they want to have parting shots or any comment to the audience before we close the room.
We would like to thank you for actually inviting us. We are really happy to share our work with everyone here, and we really are happy to hear all the comments that actually could progress our work and to think in a different perspective. And a special thanks to you, Cecile, and everyone at Quantum Photonics for actually making this happen. I really appreciate all the efforts and the way for us to promote research in a way for everyone to listen and collaborate and talk about recent advances that could contribute to humanity and also to the community in return. We appreciate it. Thank you.
Thank you. Rachel?
Yes, I can only join and add on top of what Abdul said. And really thank you, Cecile, for inviting us, and for Bob and Russell that makes it also happening with all the supporting the room and the environment. And I'm thanking the audience also for the questions. I always like to, present the research and hear the questions from the audience and learn from the questions, from this open conversation about like the future and what we can bring just by talking about these topics. And it was really inspiring to me. So thank you so much for having this platform and connecting, people that have common interests. So I really enjoyed it. Thank you so much.
Yeah, thank you again, and we'd like to. I'm very glad that you enjoyed your first clubhouse experience. We hope you come back in Quantum Photonics, and yeah, just have fun and a relaxing discussion. And we learned so much from you. And please know that we are rooting for the advancement of your research and scientific works in the future. So at this point, I'd like also thank you, Frank, for coming here today as one of the moderators. Yeah, I would have liked Frank to speak, but we don't have much time, so I'd like to give the mic to Bob now. And Bob, please pass the mic to Darcel to help us close the room. Thank you.
Thank you, Cecile. And I wanted to say thank you to both of you from everybody in the room. I've worked with some haptic commercial products in the past, but I think your work is going to bring it to a whole new level. So I look forward to what you're doing very much. And so, Mike, to you, Darcel.
Thank you, Cecile and Bob, and thank you, both doctors, for a great room tonight. To close the room, we're going to start our countdown from lucky number 8. Is everybody ready?
Hey.
8.
8.
Hey.
Kyle 7.
7.
Kyle. Good 6.
I need to fix.
Kevin 5.
5, I'm coming
in. Frank 4.
4.
Bob 3.
3 for me.
Cecile Dos Equis.
Dos Equis.
Good doctors, Rachel and Abdul. You're both numero uno. Call out our last number, please.
Uno.
Thank you so much, Rachel and Abdul. We
you.
had so much
Thank
fun.
you.
Yeah, see you soon. And
See
to
you.
everyone, see you in the next rooms. Good night.
Thank you. Good night.